Well, thank you for the invitation. Yeah, so the title of my talk is Dimensions of Quadratic Forms, Isotropic over the function field of a quadric. So the problem I'll be discussing here is an example of what people in this area refer to as an index reduction problem. So that concerns looking at the way a group, an algebraic group, can split when scalars are extended from the ground field to the function field of some variety of interest, usually a projective homogeneous variety. And in terms of algebraic geometry, this is simply about studying rational maps between a pair of projective homogeneous varieties for appropriate algebraic groups. And such problems have been considered in lots of cases, and there are lots of well-known results in this area. For quadratic forms, or the case of orthogonal groups, the fields of interest are primarily function fields of quadratic Grassmannians, varieties of isotropic subspaces for quadratic forms. But any such field up to purely transcendental extensions is just a tower of function fields of quadrics. So the primary case is in fact a case of a function field of a quadric, and this has been studied extensively going back to the 1960s, and many things are known, but there are certainly interesting problems remaining. So on the one hand, quadratic forms are rather simple to work with, but on the other hand, they're rather rich. So there seems to be plenty of non-trivial behavior remaining to observe here. So what I want to discuss concerns a conjecture that I made in a paper several years ago in 2018. And what I really want to explain here is that there's a strong version of this conjecture, which should be of at least some interest for specialists in the theory of quadratic forms. So I'm going to start here just by reviewing the original conjecture, and then eventually come to the new version of the conjecture. So the setup here is I'm going to fix two anisotropic quadratic forms P and Q. So I'll just write form for quadratic form over some field F of any characteristic, and P and Q are not required here to be non-singular forms, so just any quadratic form at all. And we consider an invariant of P, which is the largest power of 2 that's strictly less than the dimension of P, so this number 2 to the s here. And this is known to be a stable birational invariant of the form P. And that's a consequence of an important result here in this area. It's called the separation theorem. So this was first proven by Hoffmann when the characteristic of the ground field is not 2, and then later extended to characteristic 2 by Hoffmann and Legrebi. And it simply says here that if the dimension of Q is at most this 2-power invariant of P, then Q must stay an isotropic over the function field of the form P. So geometrically, what that's saying is that if you have a rational map between two anisotropic quadrics, then the dimension of the first quadric can't be much bigger than the dimension of the second one. And exactly what that means is made precise by this inequality here. So nowadays, there are lots of explanations for this result, some of them very general. So for example, it's a consequence of a general degree formula for rational maps between varieties due to Marcus Rost. But point is, for quadratic forms, it should be possible to prove much more than what you can get out of general arguments of this nature. And my goal here was to try and extend this separation theorem to a statement which attempts to understand the extent to which a form Q can become isotropic when you extend scalars to the function field of a quadric. So to generalize, we bring the isotropy index of Q over the function field of P into the game. So for the rest of this talk, I fix an integer k, which is defined as the dimension of Q minus 2 times the isotropy index of Q over the function field of P. So if you want to just think in terms of non-singular forms, this is just the width index of Q over this function field. And then the integer K would just be the dimension of the anisotropic part of Q when you extend scalars to this field. So in the general case, it's a little bit more complicated. This is just the largest dimension of a totally isotropic subspace for this form. But the point remains that when this number is large, so when you have a lot of isotropy, the number K is small. And we're primarily interested here in the case where K is small, so there's a lot of isotropy. So the question we want to address here is specifically the following. What can we say? So what are the possible values? What are the possible dimensions of quadratic forms Q which realize a given form, a given value of this integer K, taking into account some information about the form P? And this index here is only depends on the stable birational type of P. So we should consider only stable birational invariants of P. And as the first approach to this, we just consider this stable birational invariant that appears in the separation theorem, this power of 2. And the constraints coming from this invariant appear to be very simple. So the conjecture that I made in 2018 simply says the following: the dimension of Q modulo 2 to the s plus 1, so twice this 2 power invariant of P, should be between minus K and K. So I hope it's clear what I mean here. If we look at the dimension of Q and we look at integer multiples of this power of 2 here, then the dimension of Q should be in an interval centered at one of these multiples of radius K. And of course, the other possible value for the dimension is K itself. And if you're in this situation here, where the dimension of Q is at most 2 to the s, then what this conjecture says is that the only possible value for the dimension of Q is K. But if the dimension of Q is K, then this isotropy index is 0. So in other words, Q stays anisotropic over this field. So this does generalize the separation theorem, but it relates us to something which is quite striking, namely, when the value of K is low, and this is mainly what we're interested in, you see you get a rather severe constraint on the dimension of Q. It's approaching a multiple of 2 to the s plus 1. And if you go to the absolute extreme here, and you restrict, say, to the case where Q is non-singular, then you get the following statement: any anisotropic form lying in the kernel of the scalar extension map from the width group of F, quadratic width group of F, to the quadratic width group of the function field of P, has a dimension divisible by 2 to the s plus 1. So what that's saying is just if K is 0 here, then for non-singular forms, that would mean that the form becomes hyperbolic over the function field of P, and therefore represents an element in the kernel of this map. And the conjecture tells us then that the dimension must be divisible by this power of 2. Now previously, so I should say, this is proven when P is non-singular, or at least stably birational to a non-singular form in the same paper, as the conjecture is formulated. And previously, all that was really known there is that the low dimensional elements in the kernel, specifically elements of dimension less than or equal to 2 to the s plus 2, are Pfister forms. That's an old result by Fitzgerald. But there was certainly no known statement which would link some results about the kernel here to something like the separation theorem. So this conjecture provides such a link. And the point in the end is actually that the statement about the kernel here is the primary statement, since if the value of K is low enough here, then what that means is that when you extend scalars to this function field, the dimension of the anisotropic part of Q is small. And it's predicted in that case that this anisotropic part can be descended to the ground field. And there are some precise conjectures about this. And if you can descend that anisotropic part to the ground field, then you can take the form Q and translate it by that descent form, and that puts Q into the kernel of this map. So if you know the statement about the kernel, then you can readily deduce the statement of this conjecture modulo this descent problem. So as I said, there are precise conjectures about when the descent can be done, going back to work of Bruno Kahn in the 90s. But unfortunately, there are very few results about this descent problem. So the descent problem is one of the main open problems in the theory of quadratic forms, at least in my view. So I became sort of interested to know whether one can prove this a quantitative statement here, at least as some sort of evidence that this descent problem is working, given that this, at least in most cases, should follow from this observation about the kernel. Now, what I'll say, maybe come back to this at the end of the talk, is that if we assume that Q and P are non-singular, then this conjecture is proven in a lot of cases. So for example, to prove this result, it's sufficient to assume that K is at most 2 to the S, or in fact strictly less than 2 to the S, because otherwise the intervals that I've drawn here simply overlap each other and the statement becomes empty. And for non-singular forms, what we currently know is that this statement is true for all K less than or equal to 3/4 of that number. So in 3/4 of the interesting cases, this conjecture is known to be true. But what I want to talk about in this lecture is that this conjecture is somewhat suboptimal in some sense. So the issue with this conjecture is that we're only taking into account some very small piece of information about the form P. So the only invariant of P that's in the game here is this 2-power invariant, which doesn't tell us much about the form P at all. And so what we want here is some refinement of this conjecture that takes into account additional information about the form P. So there are many results in the literature of this type, and we want to sort of incorporate these results into this picture. So there are two sort of basic problems with the conjecture as it's formulated. So conjecture one, we can say one, well, first, the conjecture is optimal, but only in a special case. So the conjecture is optimal if P is a Pfister neighbor. So I'll just remind you, most people here probably know, but this means that it's stably birational to a Pfister form, so a tensor product with binary forms of dimension 2 to the S plus 1. It's well known, of course, in this case that being stably birational to such a form just means that P can be embedded up to a scalar as a subform of a Pfister form of this dimension. So remember that the dimension of P here is assumed to be strictly greater than 2 to the S. So in fact, the conjecture is known to be true for Pfister neighbors, and that's also proven in this 2018 paper. But the point is, if P is not a Pfister neighbor, then this conjecture is not optimal anymore. So it's suboptimal otherwise. So in fact, it's well known that among all anisotropic quadratic forms, the ones which have simplest stable birational type are precisely the Pfister neighbors, and there are various ways one can express that. And if P isn't a Pfister neighbor, then at least modulo some conjectural statement expressing what I just mentioned, then if you look at the kernel here, one can show that the dimensions of all forms in the kernel are actually divisible by the next power of 2. And therefore, by this translation argument, for non-Pfister neighbors, you should have a refinement of this conjecture where, at least in most cases, you can replace this power of 2 here with the next power of 2. So that's the first thing. And the second thing is that our conjecture, as I've already mentioned, is just empty. So it's vacuous if k is greater than or equal to 2 to the s. What happens in that case again is that all of these intervals just overlap and you don't get anything. But in the literature, again, there are many results which concern the case where k is bigger than 2 to the s, and these should be incorporated into the picture. So it's well known how to remedy this second problem. So to remedy problem 2, we should take into account the following invariant of P. So this is what's called the Izhboldin dimension of P, and it's defined as the dimension of P minus I1 of P, where I1 of P is the isotropy index of P over its own function field. So you take P, you extend scalars to its function field, and in the non-singular case, this is how many hyperbolic planes you can split off over that field. So it's called the first Witt index of P in that case. And it's known, again, that this is a stable birational invariant of P. And it's greater than or equal to the first stable birational invariant that we had, 2 to the s. Equality holds when P is a Pfister neighbor. But in general, this Izhboldin dimension could be larger than 2 to the s. And in fact, the possible values of this thing are known by a theorem of Karpenko. So the fact that this is a stable birational invariant of P is a result of Wishik for non-singular forms and for singular forms. It's been proven by Totaro. So for instance, if we go back to the separation theorem, there's an important result in the early 2000s due to Karpenko and Merkurjev. Again, this concerns the non-singular case, but was extended to singular forms by Totaro. It simply says if we take the separation theorem and we replace this integer 2 to the s with this Izhboldin dimension, then the conclusion remains true. So if the dimension of Q is now less than or equal to the Izhboldin dimension of P, then Q stays anisotropic over the function field of P. So we should have some refinement of our conjecture, for instance, that takes this statement into account. And as I mentioned, there's another result essentially, or in most cases due to Karpenko, which determines all possible values of this Izhboldin dimension. And we can think of this as an instance of the same problem that we're looking at, just in the case where, so this concerns the isotropy index of P over its own function field. So the problem of determining the values of this invariant is just, again, looking at the problem I formulated in the beginning in the case where P is the same as Q, right? So Q is just equal to P. So there should be some statement that takes this result of Karpenko-Merkurjev and Totaro into account, this result of Karpenko into account, and other known results as well. And this was clear from the very beginning, but at the time when I first found this conjecture, it wasn't clear to me at all what such a generalization of this should look like. But last year, I've found a proof of this conjecture in a test case, and this is the case where Q is a so-called quasilinear form over a field of characteristic 2. And in that case, the proof reveals a much stronger conclusion than what you can get, or than what conjecture 1 here predicts. And this involves some invariants of the form P, which are not defined in the general case. But when you analyze the contribution from the invariants which are defined in the general case, you end up with a refinement of this statement, which should be true for all forms Q and all forms P. And this is exactly the generalization of this conjecture that we're looking for. Now, this result in the quasi-linear case is something I mentioned very briefly in a couple of Zoom talks. And in fact, but without giving any details. And in fact, the paper also hasn't appeared yet, but it should appear very soon. So I thought in this lecture, I would give some more details about this result. So I'm now going to pass to this very special case. So this is in characteristic 2, but even if you don't care about quadratic forms in characteristic 2, the point is that the conclusion leads to some conjecture, which should be quite interesting for specialists in the theory of quadratic forms. So I'm now going to suppose temporarily that the characteristic of f is equal to 2, and then the theorem is that if Q is so-called quasilinear form, so what that means is it's a diagonal form. So that just means the diagonal part of some symmetric bilinear form, so a weighted sum of squares. So of course, in the good characteristic, every quadratic form is isometric to a form of this type. In characteristic 2, these are only a very special class of forms. So by the binomial theorem, any such form is additive. You don't have this correspondence between symmetric bilinear forms and quadratic forms in characteristic 2. And geometrically, if you consider the quadric defined by a form of this type, if you extend scalars to an algebraic closure, you'll just end up with a double hyperplane. So the quadrics defined by such forms are some very special variety, so they don't have any smooth points at all. So in the usual theory for non-singular forms, to prove results on conjecture of this type, we have to, or the only methods we have at the moment are algebraic geometric methods. So looking at algebraic cycles or algebraic cycles modulo 2 on quadrics or products of quadrics or quadratic Grassmannians. So here it's sort of hopeless to use such techniques, but it turns out these forms are simple enough that you can just argue by direct algebraic means, but they're not simple enough that the thing just becomes completely trivial. And the forms are interesting enough that analogs of many of the main known results for non-singular forms are also true here. So this becomes an interesting testing ground for conjectures of the type that I've just mentioned. Now, the first thing to say is that in this case, if our form P is non-singular, then Q simply can't become isotropic over the, if the form P is not also quasi-linear, then Q can't become isotropic over the function field P. If P is not quasi-linear, right, then the variety, the quadric of P is a generically smooth variety, and there's no way to write down a map from a smooth variety to a variety which has no smooth points. So to prove this theorem, we can also assume, without loss of generality, that the form P is a quasi-linear form as well. And in this case, we can introduce some new invariants of the form P. So this is now dealing with the case where both P and Q are quasi-linear forms. So we want to bring this Izhboldin dimension that I've mentioned before into the game, but first we consider another invariant. So we consider the following integer. So in the literature, this is called the norm degree of P. So I'm denoting it here, n degree P. And this is basically the degree of a certain finite, purely inseparable extension of the field F. So this extension K is just the smallest extension of K that contains all square roots of products of two values of the form P over the ground field F. So X and Y here are values of P, and the value set I denote here D of P. So if P is, let's say we scale P so that it now represents 1, and then we choose coordinates, so we get an explicit representation of this form P, then this field K is nothing else but the field we get by adjoining the square roots of these coefficients A1, A2 up to AN. So we're interested in the degree of this purely inseparable extension of F, and just to make life a little bit easier here, I'm going to take, so the degree of this thing is a power of 2, and I'm going to take the exponent here. So I'm taking the base 2 logarithm of this degree. So this integer is known by a result of Hoffmann and Agrebe to be, again, a stable birational invariant of the form P, and it's greater than or equal to s plus 1, where s is the same integer that I've defined previously. So again, the dimension of P here is strictly greater than 2 to the s, but less than or equal to 2 to the s plus 1. And you can ask, when does it take the value s plus 1? So in some sense, it should happen when this form P has the simplest stable birational type, and that's exactly what happens. So the norm degree of P is equal to the minimal value s plus 1 if and only if P is now a quasi-linear Pfister neighbor. So that's defined as before. It's just we replace Pfister forms now with quasi-linear Pfister forms. So a quasi-linear Pfister form would be the diagonal part of a Pfister symmetric bilinear form. So it's just, again, a tensor product with binary forms, but these forms are now quasi-linear. And a quasi-Pfister neighbor is just a quasi-linear form which is stably birational to a quasi-Pfister neighbor. So for forms which are not quasi-Pfister neighbors, the norm degree will be larger. And as an extreme example, so the largest value of the norm degree is just the dimension of P minus 1. And that happens, for instance, if P is generic. So when I say P is generic here, I mean, for example, that P is just the diagonal form whose coefficients are given by algebraically independent variables. So in this case, the norm degree of P is as large as possible. It's just the dimension of P minus 1, which is usually far bigger than s plus 1. Now, this is one of the invariants that will play a role here, but we now want to bring this Izhboldin dimension into the game. So this comes into it in the following way. So if we extend scalars to the function field of P, then P becomes isotropic. And with decomposition for quasi-linear quadratic forms now looks as follows. So it will decompose as the sum of some anisotropic form P1 and then a 0 form of dimension equal to the integer I1P. So this is, again, just the index of P over this function field. So there's no hyperbolic planes here. This is simply taking the vector space on which P is defined and decomposing it as a sum of a maximal totally isotropic subspace, which will have this dimension, and then some complementary form P1. So this is for some anisotropic form P1. And we can note here that the dimension of this form P1 is the dimension of P minus I1 of P, which is exactly our Izhboldin dimension. So the Izhboldin dimension will enter the game here as the dimension of this form P1. And we can also remark here that the norm degree of the form P1 is just the norm degree of P minus 1. So the norm degree goes down by 1 when we extend scalars to this function field f of P. Now, the idea here is that we're going to introduce a new invariant, which is not defined for quadratic forms in general, only for these quasi-linear forms, which remembers the norm degree of P, but also takes into account this Izhboldin dimension. And this is defined in the following way. So we introduce a new invariant, which in this talk, I'm just going to denote delta P. And this is a subset of the integers from 0 up to the norm degree of P minus 1, which is the norm degree of this form P1. And we define it in the following way. So if we take an integer r in this set, then it's an element of this invariant delta P if there exists an anisotropic quasi-linear form phi over the function field of P, such that First, P1 is a subform of this form phi, and the codimension of P1 in this form phi is less than 2 to the r. And second, this form phi is a multiple of a quasilinear Pfister form of dimension 2 to the r. So what I would say here is that the form P1 is what I would call a close neighbor of this form phi. So you can show in this case that the form phi is uniquely determined up to isometry. The Pfister form here is not uniquely determined, but the form phi is. And the form P1 is stably birational to the form phi. There are possibly other subforms of phi which are also stably birational to phi, but here we have this codimension condition. So these are subforms stably birational to phi which have sufficiently small codimension. So we have this new invariant here, and we have a result again which says that this form, or this invariant delta p, is in this case a stable birational invariant of p, and this is in fact precisely the invariant which controls what can happen when you consider the isotropy of quasilinear forms under scalar extension to the function field of p. So let me just mention again that the same two examples as before. So if p is a quasilinear Pfister neighbor, then this invariant looks as follows. It's just all the integers from 0 up to the norm degree of p minus 1, which in this case is just s, right? So in this case, this invariant contains a lot of elements, but of course, the more complicated your form is, the less and less likely it is that there will exist any such embedding here. And if you go to the extreme case where p is generic, then the only elements of this invariant are 0, and then the dimension of p minus 2, which is again the norm degree of p minus 1 in this case. Okay, so for sufficiently generic forms, this invariant will in fact just contain some information about the dimension of p, but for forms with a sort of simpler stable birational type, there will be other entries in this set. Okay, so I'm now going to formulate or state the theorem, which will lead to the new version of our original conjecture. So I need one additional piece of information. So for each integer r greater than or equal to 0, we let y sub r be the unique integer such that the Izhboldin dimension of p is greater than 2 to the r times yr, but less than or equal to yr plus 1 times 2 to the r. So the connection here is that this upper bound here should be the dimension. So in the result we're about to formulate, this upper bound here appears as the dimension of one of these forms phi here, which is divisible by a Pfister form of dimension 2 to the r. And the form P1 here is a close neighbor of this form, so it has codimension less than 2 to the r, and the dimension of P1 is exactly the dimension of this, exactly this Izhboldin dimension here. So this here is the dimension of P1. So the theorem is now the following. So we want to ask the same question as before. If I take a value of this integer k, I want to know what are the dimensions of the quadratic forms that realize this value of k, taking into account information on this form p. And the information we now want to take into account is exactly this invariant delta p that I've just defined. And here, the solution to the problem is the following. So in order to get something non-trivial, we have to assume that k is sufficiently small. And here that means that k is strictly less than the Izhboldin dimension of P. Then the possible values of the dimension of Q are as follows. So in the first conjecture, I was working modulo 2 to the s plus 1. And now I'm working modulo 2 to the norm degree of P. So remember, in this case, this integer is exactly s plus 1 when P is a quasi-Pfister neighbor, but otherwise it will be strictly greater than s plus 1. And for a generic form, it will be a very large power of 2. And modulo this thing, the dimension of Q is now in an interval of the following type. So it will be y sub r, where this is this integer I've just defined, times plus some integer x times 2 to the r minus 1, now minus k, up to x times 2 to the r plus 1 plus k. And this is for some r and x satisfying the following conditions. So first of all, the integer r has to lie in this invariant delta p. And second, there's a constraint on the value of this integer x. So this looks a little bit more complicated. So x has to be less than or equal to y sub m plus 1 times 2 to the m minus r minus y sub r for some integer m, which is again in this invariant delta p, but is now greater than or equal to the following integer. So r plus the integral part of base 2 logarithm of x and less than or equal to r plus x. Okay, so this obviously looks very technical and complicated, so let me just make some remarks here. So one integer which is always in this invariant delta p is just the so the maximal value, the norm degree of p minus 1. And in that case, this integer y r is 0, and this condition will tell you that x has to be 0 as well. And 2 to the r plus 1 will be just this integer here, 2 to the norm degree of p. So in that case, this interval here just becomes minus kk, and then we're working modulo this integer here. So we just get the same statement as for conjecture 1, but with a much better exponent here for this power of 2. And for most forms, the only value of this thing here, the only non-zero value, will in fact be the norm degree of p minus 1. But so for some other forms, there will be other values of this set here, which are giving some additional possible values of the dimension of q. But even if there are additional values here, the point is that in order for this interval to be non-empty, the value of k has to be reasonably large. So unless k is greater than or equal to 2 to the r times this integer yr, this interval is just empty. So in fact, what we get here is something which looks like the original conjecture, but with a better exponent here. But then there are some extra values appearing along the way. So I'll go to an example in a moment. So I was going to say something about the proof of this theorem, but I can see I'm running a bit low on time. But I'll just say that the proof of this is elementary, but rather tricky. So it involves some kind of complicated induction argument. And these integers here, x times 2 to the r plus 1, these appear as dimensions of some quadratic forms which are divisible by Pfister forms of dimension 2 to the r plus 1. Okay, so everything is quite explicit here. And in fact, this statement is an optimal statement, so you can show that all of these values are really possible. The proof, in fact, shows you how to construct forms Q which satisfy, which realize these permissible dimensions given by the statement of this theorem. So this is somehow a very complete solution to this original problem that we were looking at. Okay, but the interesting
one
thing,
interval or several intervals?
several intervals, yeah. So there are multiple intervals here so you get a separate interval for each value of this invariant, right? But for most forms P, there will only be a couple of integers in this invariant, so you'll only get some very small intervals. And I should say that it's quite possible that for different values of R, one of the intervals is just different values of R and X. Some of these intervals are just contained in each other. So actually, it will usually just be some very small collection of intervals here. Right now, the interesting question is, what does this mean, right, for the sort of general theory here? And so let's now return. So relax the assumption on the characteristic of our field F. And I'm now going to assume that neither Q nor P are quasi-linear forms. So there's one case. So I should say, by the way, this theorem here proves the original conjecture in the case where Q is quasi-linear, and it's a much stronger result than that. So one case I'm excluding here is the case where Q is not quasi-linear, but P is quasi-linear. There's no reason to exclude that case, but I just don't know how to handle that case at all. So I'm just removing it from my considerations. Right, so what can we do here? So in the general theory, so in this case, we have no analog of this invariant delta P. So we don't know how to replace this, but what we do have is the Izhboldin dimension, which constrains this invariant delta P. And so we can ask, what is the contribution here coming from the Izhboldin dimension? And when you analyze that, you get an interesting looking statement. And the second thing we can do is we can make the distinction between Pfister neighbors and non-Pfister neighbors. So I mentioned the original conjecture is suboptimal if you consider the case of non-Pfister neighbors. And here, the case of quasi-Pfister neighbors is separated from the case of non-quasi-Pfister neighbors by this norm degree. So the norm degree is minimal for quasi-Pfister neighbors, but otherwise it's bigger than the minimal value. So we can analyze what happens in that case as well. And what we come to is a conjecture, but in order to formulate a conjecture which you actually have some chance of proving, I need to just introduce some auxiliary invariant, which due to time constraints I can't define, but let me just say, so there is an invariant in this case. Again, it's a stable birational invariant of P, which is a positive integer which is divisible by 2. So I'm going to denote it here, rank UP. So it's an even positive integer. So what this is in the case where P is non-singular, this UP is a certain canonical direct summand in the motive, the Chow motive of the quadric defined by Q. It's called the upper summand. It's known to be a stable birational invariant of P. Again, by a result of Wishik, at least again in the non-singular case. And what the rank means here is over a splitting field, this motive decomposes as a direct sum of Tate motives, and the rank is just a number of Tate motives in that decomposition. So when P is a Pfister neighbor, this motive is known. It's a Rust motive. So a Rust motive has rank 2, so it's over a splitting field a direct sum of 2 Tate motives. So this invariant takes the value 2 when P is a Pfister neighbor. And conjecturally, that's the only case where this rank can be 2, at least for non-singular forms. It's the conjecture of Wishik, but it's in fact highly non-trivial problem and remains open. But in principle, it gives us a geometric way to distinguish between Pfister neighbors and non-Pfister neighbors. So for singular forms, it's still possible to define this invariant. You don't have any more, you can't, in the conventional sense anyway, talk about the motive of the quadric P, but it's still possible to define this thing just by considering algebraic cycles on the product of P with itself. And again, even for singular Pfister neighbors, you can prove that the rank of this thing, that this number is 2 in that case. But for non-Pfister neighbors, if the form is sufficiently non-singular, then the rank shouldn't be 2. So the conjecture that is proven, basically, or the analog of it is proven by the theorem above for quasi-linear forms is now the following. Assume again that the integer k is strictly less than the Izhboldin dimension of the form P. Then the dimension of Q. So we now again want to look what are the possible dimensions of the forms, realizing a given value of k, taking into account this Izhboldin dimension of P. And we get the following statement. So in the original conjecture, we work modulo 2 to the s plus 1. Now we work modulo 2 to the s plus 2. And the dimension of P is again modulo this number in the intervals of the same type. So the integers yr are defined as before. And so here we just get the same expressions. But this is now, we don't have this invariant at delta P. So this is just for some integer r, which is at most s plus 1, and some integer x, which is at most 2 to the s minus r plus 1. So that's the general conjecture, but we can also look at the case where P is not a Pfister neighbor. But for me, I'm going to formulate this in terms of this invariant here, which again, for non-singular forms, this is the rank of this upper direct sum and in the motive of the quadric defined by P. So if the Izhboldin dimension of P takes its minimal value, which is 2 to the s, and the rank of this upper summand, if you like, is strictly bigger than 2, then we have some further restrictions on the possible values of r and x here. So again, this is a bit technical to write down, but I'll do it anyway. So r now has to be less than or equal to s minus 2. X has to be either less than or equal to this power of 2 or greater than or equal to that power of 2 plus the previous power of 2. And the pair Rx, there are some other excluded values. So it can't be 2 s minus 2, 2 s minus 2, sorry, 3 s minus 2, or 4 s minus 3. Okay, so again, this looks like a mouthful, but I just will jump to an example to show you what this looks like. So here we take a form P of dimension 17, which is not a Pfister neighbor. So the Izhboldin dimension of P is 16 in this case. So we get a conjecture up for all values of K up to 15. And if you look at the values of K up to 11, so the dimension of Q mod 64 is just, again, in the interval from minus K up to K. So this is just conjecture 1, but now with a better exponent here. So in the first conjecture, it was 32, but now it's 64. But when you make K a little bit bigger, you get some extra values. So when K is 12, we have the same things as before, but now there are 2 extra values here. When K is 13, there are 4 extra values. When K is 14, there are 8 extra values. But even when we have this large value of K here, 14, you can see that many things are excluded, like 24, 28, 30, 32, and so on. And these would be permissible if P was a Pfister neighbor, but otherwise they're out of the game. And I can see I'm basically out of time, but what I'll say about this conjecture, so why should you believe it? Well, first of all, it contains several known results in the literature. So the theorem of Karpenko-Merkurjev and Totaro I mentioned in the beginning, which says that if the dimension of Q is at most this Izhboldin dimension, then Q stays an isotropic over this field. This is a particular case of this conjecture. Karpenko's theorem on the possible values of the Izhboldin dimension is also a special case of this conjecture. And then there are some other results extending those due to myself, which are also special cases of this conjecture. So just in the last minute, sorry, I'm already over time, I'll just mention what the main known result of this on this conjecture is. So you can prove various things, but the main result concerns the case where both P and Q are non-singular and uses geometric methods in a heavy way. So Steenrod operations on Chow groups modulo 2 for quadrics and products of quadrics. So I have a paper from 2 years ago, which proved conjecture 1 under a certain constraint on the integer k. If you examine the proof and you add some additional arguments, you see that you can prove the conjecture 2 under the same constraints on the integer k. So the main result, so this is 2018 plus some, not 18, sorry, 2020 result plus some extra arguments shows that conjecture 2 is true when P and Q are non-singular and the dimension of P is strictly greater than 2 to the K minus 2 to the S plus 1. So one case where that's satisfied is where the integer K is at most 3/4 of 2 to the S. And as I said, that proves conjecture 1 in 3/4 of the cases where it's interesting. Okay, so this obviously looks extremely technical to look at, but the main conclusion is that there's some interesting generalization of this original conjecture, which takes into account additional information on this form P, and if true, recovers several important and well-known results in the literature. And this problem appears to be quite interesting and related to interesting, open and important problems in the subject. And at least for me, it seems to be, it's not so easy to prove this, even making use of the sort of substantial geometric machinery which is available in the non-singular cases. Okay, so I'm sorry for going a little bit over the time, but I'll stop here.
Thank you. Are there any questions?
Yeah, if I may ask.
Please.
Right, it's about this invariant delta P. If we consider quasilinear forms, no, we have the analog of the result of the theorem of Karpenko describing the first high-width index.
Yeah.
Is it true that in all these cases you can realize it by embedding into a product of form proportional to a twistor form, or not?
You mean, are these powers of 2 explained by?
Yes, yeah. No, the values of I1.
Yes, that's in the quasi-linear case. Those powers of 2 arise as. I mean, these multiples of powers of 2 arise as dimensions of forms which are divisible by quasi-linear Pfister forms of appropriate dimension. So in this case, everything is proved in some sort of reasonably concrete way. And in fact, if you look at the proof of the theorem, you can almost believe that in that quasi-linear case, it may be even possible to classify the forms Q that realize some given value K, at least if the value of K is sort of sufficiently small. That's not what I've done here, but I only get something weaker. But yes, everything is explained there by this embeddings into forms divisible by some quasi-linear Pfister forms.
Thank you. Thank you.
Any other questions? If there are no other questions, maybe I can ask about conjecture 2. I'm not entirely clear how you choose R and X here. Are they arbitrary, just subject to these constraints? So you get an interval,
yes,
for each pair?
Yes, they're arbitrary. So in the quasi-linear case, you see that there are constraints on R and X coming from this invariant delta P, but we don't have this invariant delta p in the general situations. We can't put any constraints on R and X. But I should say here that in the quasi-linear case, right, if you just take these constraints here as they're written, so the very limited constraints, one can still show that actually the result is optimal. So all the values can be realized. Unfortunately, for non-singular forms, I just don't know whether this conjecture is optimal or not, because, as I said, in the quasi-linear case, the proof somehow shows how you can construct all the forms that realize the permissible dimensions here. And you can write down exactly the same forms in the non-singular situation, or at least the analogs of those forms. But it's less obvious to see whether they actually realize the given value of k or not. So yeah, here there's basically no constraint on R and S other than what we have here, unless we want to consider the situation where we have a form which is not a Pfister neighbor, but for which this Izhboldin dimension takes the smallest possible value. Then we can impose some additional constraints. So basically, in the quasi-linear case, if these constraints were not satisfied, then you can prove that if we're outside of these cases here, then you can prove that the form P is a quasi-Pfister neighbor. So the same thing should hold here.
So should we understand conjecture 1 as sort of the first approximation? We have this interval, this range, modulo 2 to the power s plus 1, and then for conjecture 2.
Yeah, so what?
And then is there conjecture 3, which gives us the range modulo 2 to the power s plus 3?
No, that's an interesting point, because if you go back to the quasi-linear case, so I mentioned somehow if you look at this generic forms in the quasi-linear case, as I said, this invariant delta p will be sort of trivial. The only element in this delta p will be a very large number, the dimension of p minus 2. And when you look at what the theorem says in this case, it'll just say that the dimension of q is between minus k and plus k modulo this extremely large power of 2. So you might predict that if you take, say, a generic form, sufficiently generic form in the non-singular case, say, that you get the same thing, that the dimension of q should be between modulo some very large power of 2 between minus k and k. But in the non-singular case, something weird happens, which it's sufficient to think about the kernel of the map on the bit group. If we look at sort of the dimensions of anisotropic forms which are in the kernel here, the original proof of the separation theorem by Hoffmann uses an algebraic construction of embedding forms into Pfister forms. And this construction somehow shows that the dimensions of, if you look at the possible dimensions of forms in the kernel here, it's completely, or it appears to be unstable under very gentle extensions, so unirational extensions, and in some cases even purely transcendental extensions. So if you make a gentle extension of the ground field, the point is that you can always find in the kernel of this map an element of dimension 2 to the s plus 2. And for the invariants of quadratic forms that we know, they're all completely stable under such extensions. So if we only take into account invariants of P, which are stable under unirational extensions, whatever, then the best you can hope for in the general case is this exponent to be 2 to the s plus 2. So that's where it diverges from this quasi-linear case, where you can always make some improvement here. But with known invariants of quadratic forms in the general case, you cannot do any better than this. So
I see.
there is no conjecture 3, unless you bring some new things into the game.
Like maybe the invariant I2 of P rather than I1?
I mean, so like I said, yeah, I don't think such invariants can have any further bearing on what can happen in this case. So yeah, even if you take some form which is sort of generic in many sort of in any sort of respect that you can imagine, I don't think you can improve upon what's stated in the conjecture.
Okay, thank you. Are there any further questions?
So do I understand correctly that there is no hope to define any traditional version of delta P invariant? So it exists only for quasilinear.
I don't say it exists. I mean, I don't know. Maybe there is something.
But is it possible to define? No, is it theoretically possible to define something maybe by some different methods, something which would play a similar role? Which you
yeah, of course, it would be great if it was possible to do such thing, but I just don't know. Yeah, as you know, I mean, somehow here, in the quasi-linear case, somehow what happens is that the powers of two really arise as dimensions of Pfister forms, and as you know, the early attempts to prove statements like this by Hoffmann and Izhboldin, people like that, they also tried to do it using Pfister forms. These Pfister forms were appearing not over the ground field, but over some very transcendental extension, right, of the ground field. So it's maybe possible that you can somehow bring Pfister forms into the game by permitting yourself to make some extensions of this type where the situation simplifies. But I don't know of any way to produce some invariant that plays the role of delta P.
But do we have hope that statements similar to a quasi-linear one can hold in this case?
I don't know, to be honest. So like I said, no, I don't. Yeah, I unfortunately I can't give a good answer to that question. So I just don't know what you can expect in general. So as you know, if you take the case of the kernel on the map, the kernel on the bit group, when you go to the function field of P, we have almost no computations of that thing. So I just don't know what.
Okay. No, thank you.
Any other questions? Okay, if there are no further questions, let's thank the speaker again.